Hi everyone, and welcome back to the Introduction to Emerging Contaminants course offered by the REMEDI ITN. This is the second lecture part of the introduction to the course, and it will be a short overview over the main existing conventional water treatment processes. So, we left off by saying that the currently best available technologies, or BATs, for the removal of emerging contaminants are adsorption onto activated carbon, advanced oxidation processes such as ozone treatment, and membrane systems such as reverse osmosis. Nonetheless, we also highlighted the need for a case-specific assessment of the most suitable technology to be applied in any given case. Differences in the incoming water or the existing and planned infrastructures are among the factors that may favor a technique over the others. Overall, the best course of action is always a multi-layered approach, able to cover the widest range of compounds and reduce risks. These layers often include conventional water treatment plant processes, which at times are sufficient in and of themselves to remove some contaminants. Thus, understanding what these systems are and how they may contribute to the removal process is necessary for proper planning of a remediation effort. In the following, a brief overview of the most common conventional water treatment processes will be provided. So, water treatment plant processes may be subdivided into two main routes of treatment. Purification or wastewater treatment, aimed at sanitizing heavily contaminated wastewater before its safe reintroduction into the environment, and potabilization or drinking water treatment, aimed at sanitizing water from different sources such as rivers, lakes, springs, or wells for human and industrial use and consumption. These processes are part of what's called the integrated water service, pictured in the image on the right. These processes have all different aims, treat water with different initial characteristics, and thus different from each other in some regards when it comes to treatment processes. So let's start from purification or wastewater treatment. Wastewater comes in two main forms, which may change etiquette depending on where we are, but the concepts are generally the same. We can identify the so-called black wastewater, which is wastewater coming mainly from anthropic uses, such as domestic or industrial wastewater, and it's generally heavily contaminated. On the other hand, we can identify white wastewater, which is mainly of meteoric origin and thus, such as water runoff from roads, and is thus less contaminated. In mixed wastewater, the two above are merged and mixed. The main objective of wastewater treatment is the removal of pathogens, organic matter, excess nutrients, and contaminants, and their return to safe levels before its eventual reintroduction into the environment. In this table, you can see a summary of the most common wastewater treatment processes. We'll look over each of them independently in the next few slides. Overall, through these processes, most natural and anthropic contaminants are successfully removed. Although not all of these processes need to be combined together every single time, but any combination of these, depending on a case-specific assessment and particularly on the quality of incoming water, may be applied to ensure adequate quality levels and an efficient treatment, depending on the case. In particular, some of these processes are also shared with the potabilization process. This can include, for example, disinfection and filtration processes. The first treatment process that wastewater generally goes through is an initial screening of solid waste and other unwanted materials. This is generally achieved by mechanical means, by means of metal sieves and conveyor belts, leading the waste away for disposal. After this initial screening of macroscopic solid waste, such as branches and leaves and other solid material, smaller particles, such as sand particles, are removed by descending. Descending is achieved by aeration of the water and generation of air bubbles, which favor the separation of the sand from the water. At the same time, aeration also favors the separation of fatty and oily substances, which float on the surface and can thus be separated, if they have not yet been separated by the earlier processes. After these treatment processes, water is then ready to move on to the first sedimentation process, also called primary sedimentation. The sedimentation process is one of the most common and important processes in wastewater treatment. During primary sedimentation, slow and steady water flow conditions favor the sedimentation of suspended solids on the bottom of a tank called the sedimentation tank. This process can be favored by the addition of substances called flocculants, able to promote the aggregation of suspended solids. As a result, these heavier aggregates have an easier time settling and falling to the bottom of the sedimentation tank. Aggregation can also be promoted not only through chemical means, but also through physical means, such as by changing the pH of the water matrix. This process usually precedes biological water treatment and sometimes often follows it, in which case we may want to speak of secondary, tertiary, or final sedimentation. This process may also be referred to as clariflocculation. Biological treatment is the primary and most common treatment process in conventional wastewater treatment plants, or WWTPs. During biological treatment, microbial communities hosted in large tanks and maintained in ideal living conditions degrade the available organic matter and nutrients in the wastewater, thus restoring it to its natural ideal conditions. Particular focuses of this treatment are the levels of nitrogen and phosphorus, because of their potential influence of these elements, in particular on the proliferation of algae and other living organisms at the outlet of the wastewater treatment plant. As such, during biological treatment, the natural biodegradation processes that this organic matter and nutrients would naturally undergo in a matter of days or weeks are accelerated and achieved in a matter of hours by maintaining the ideal living conditions for these microbial communities. This process is often followed by an additional sedimentation step to recover the microbial communities which might potentially be lost during the treatment, as well as disinfection and filtration. Disinfection is an important and common step in the wastewater purification process. During disinfection, living organisms such as bacteria, viruses, protozoa, helminths, and algae are removed by treatment with disinfectant agents. Commonly used disinfectant agents include chlorine and its derivatives, UV lamps, and ozone, with each process providing certain advantages and disadvantages, and the choice being thus down to a case-specific assessment. In particular, factors which may influence the choice are the type and initial conditions of the water treated and the needs of the water network. A short recap of these different disinfection processes with their pros and cons is provided in the next slide. Filtration is an ancillary step of wastewater treatment, often included in many wastewater and drinking water treatment plants. During filtration, microscopic suspended matter, most remaining fine particles, and even dissolved contaminants are mechanically removed by filtration by a porous medium. Commonly used porous media include sand and gravel in natural filters, filters made of fabric, as well as activated carbon, an exceptional porous material for the removal of a wide range of dissolved contaminants, including emerging contaminants and other micropollutants. Earlier, we said that emerging contaminants, such as PFAS or pharmaceuticals and personal care products, or PCPCPs, can often be found in drinking water. Potabilization processes, or drinking water treatment, aims at sanitizing water for human use and consumption. Whereas the quality of the outgoing water for human use is mandated by regulations and is thus constant, what is not constant is the quality of the incoming water, which can vary significantly depending on the source. Springs have generally the highest quality waters found in nature. This is thanks to the good physical-chemical properties attributable to the relatively lower anthropic contamination these springs are generally subjected to, while still being vulnerable to potential contamination by microorganisms or natural sources. Springs often only require disinfection to be fit for human use, although other processes such as flocculation and sedimentation may sometimes be necessary. Water wells tapping into groundwater sources are among the most common sources of water for human use. The quality of groundwater is heavily dependent on local conditions, and the case-by-case evaluation of the necessary treatment processes is thus often required, particularly for groundwater wells. The filtration of the water by the soil above the groundwater can often positively contribute to the quality of the water, although it may still be vulnerable to microorganisms and excess contaminants. Depending on the case-by-case basis, a full potabilization process may be required. Lastly, surface waters, such as rivers and lakes, tend to be the waters most susceptible to natural and anthropogenic contamination, thus often requiring full potabilization processes, including advanced treatments, such as filtration by activated carbon, ozone, or filtration. Speaking of advanced treatments, we have introduced earlier that many energy contaminants evade most conventional purification and potabilization treatments, and thus end up in drinking water as well as natural waters. There are, however, some processes which have shown significant promise in the removal of energy contaminants from waters, and these include adsorption by GAC or PAC, or granular activated carbon and powdered activated carbon, membrane systems, and advanced oxidation processes, or AOPs, among which is included ozone treatment. Among the advanced treatment processes for emerging contaminants that we have been talking about, activated carbon is among the best available technologies for emerging contaminants removal. Adsorption by activated carbon is a type of mechanical process to be included into filtration regimes. Dissolved contaminants are actively removed from the water matrix by adsorption and retention on the surface of highly porous solid materials, in this case activated carbons. Activated carbons are prepared from a carbon source, which may be wood, coal, or coconut shells, through an activation process, which increases the surface area of the product and thus its ability to absorb and retain contaminants. By adsorption by activated carbon, removal of a wide range of dissolved contaminants may be achieved, including toxins, algae, pharmaceuticals, and industrial additives, as well as disinfection byproducts. An example of the application of activated carbon in the removal of energy contaminants can be found in the PFAS crisis in the Veneto region in northern Italy, which occurred around 2013. In this case, concerningly high levels of PFAS in the drinking water of the region were found, and the local authorities chose to intervene by setting up additional activated carbon filtration systems at most potabilization plants, which lowered successfully PFAS concentrations in drinking water below the threshold levels. There exist many varieties of activated carbon, differing in structure, porosity, origin of the material, as well as potential biological activation, all characteristics and processes which influence the functionality of the product and its specificity. Membrane systems are among the most effective and innovative means of advanced contaminant removal from waters. In membrane systems, a semi-permeable membrane of variable porosity and surface charge is used to mechanically separate dissolved contaminants from water under pressure. Based on the size of the pores of the semi-permeable membrane, and thus the selectivity of the removal process, we can define micro, ultra, and nanofiltration, as well as reverse osmosis, which can remove almost all dissolved particles from the water matrix. These are later concentrated into a highly concentrated waste solution to be disposed of. Reverse osmosis, thanks to its capability to remove dissolved solutes from water, has been used extensively for water desalination and the removal of solids from seawater. Finally, among the most commonly used treatment processes for emerging contaminant and micropollutant removal, as well as being considered among the best available technologies nowadays for a large-scale removal process, are advanced oxidation processes, or AOPs. During advanced oxidation treatment, the chemical degradation of contaminants is achieved by means of oxidation. Oxidation can be achieved by an oxidant supplied as is, or on the in situ or local formation of radicals from a primary oxidant, given an energy source and with or without the aid of a catalyst. The most common advanced oxidation process is ozone treatment, commonly applied for the removal of a wide range of contaminants, including industrial and pharmaceutical additives. Advanced oxidation processes have shown promise in the removal of many energy contaminants, including drugs, pesticides, as well as herbicides. So, each of the three processes that we have looked so far in terms of advanced treatment strategies for emerging contaminants has its merits, advantages, and disadvantages. Not all processes can be applied in any given case. There are some processes that cannot be applied, for example, with a given incoming water type or the characteristics of the incoming water. And thus, a case-specific assessment of the best removal strategy for the case is often required and necessary.